dumbbells?
I can.
Yeah, okay, we should go down there and get them if you want them.
Okay.
So you don't have to save up and get them. Okay, so we left off today, we were talking about cardiac output. We were talking about the kind of the physiological factors that are going to play a role in determining what cardiac output is and determining the changes in cardiac output that are going to happen as it increases during exercise. So last time we spent time talking about heart rate, okay? So that component of cardiac output, remember there's a linear relationship between heart rate and cardiac output. So today we are going to talk about the other side of this. We're going to talk about stroke volume, okay? And so in many ways, the regulation of stroke volume is more important and more complex than the regulation of heart rate, okay? That's not to say that we couldn't get way into the weeds on kind of sympathetic and parasympathetic control of heart rate, but in general, things that are going to be different between people, that are going to have actual performance consequences and actual training kind of adaptation consequences, are most often going to occur on the stroke volume side of things, okay? So we're going to break kind of into four kind of big, broad areas, things that play some role on stroke volume, and then within each area, we will talk about what are the physiological factors and things that are going to underlie each one of these, okay? So we're going to start off with something called preload, okay? Something called preload. So preload is basically end diastolic volume, okay? That's the best way to think about it. Preload is how much blood gets into the left ventricle while it is filling up right before it contracts, okay? And so what I can tell you then is that if I can make preload go up, I can make stroke volume go up. If something happens that makes preload go down, stroke volume will go down. And so as stroke volume changes, so therefore will cardiac output, okay? So if we make a list of things that may play some role on altering preload. Cardiac output itself, okay? As cardiac output goes up, preload also tends to go up, okay? Your posture can affect preload. If I want to make Pearson's preload go up right now, we're going to have him go do a handstand on the wall, okay? We're going to go and increase, because that's going to increase venous return. So posture matters because we're working against gravity. That's related to these other ones. Venous tone matters. Remember, I hate the word tone when it refers to muscles, okay? When it refers to muscles. But in the cardiovascular system, tone is going to denote for us some level on a spectrum where we are between fully relaxed and dilated vessels and fully kind of squished down, contracted vessels. And you may be thinking to yourself, Dr. Black, I didn't think that veins could have tone. I thought it was only the arteries and the arterioles. Well, veins have a little bit of smooth muscle on them. They can change their diameter a little bit, okay? Not to nearly the same extent that especially arterioles can, but they can do a little bit. So if I squeeze on the veins a little bit, I raise the pressure in those veins and it helps force blood back towards the heart. Okay? Blood volume. You have more blood volume, you're going to tend to have a bigger cardiac output. You have more blood volume, your preload's going to go up. Okay? Priming by the atria, right? So if I can sort of increase atrial contraction strength and put more blood into in from all of that, that's going to work. The muscle pump and the intrathoracic pressure are also going to play a role. So we're going to talk about each one of these a little bit more, but I want you guys to appreciate that we're going to group a lot of these things. The biggest thing that affects preload, the biggest overarching thing that affects preload is something called venous return, okay? Venous return. And that just simply means how much blood is going to get back to the heart in a given period of time. Out of the veins, back to the heart, okay? If that goes up, then preload is going to tend to go up. Venous return goes up, okay? And And so a lot of the things that you're going to see, intrathoracic pressure, the muscle pump, venous tone, posture, are all going to be things that will alter venous return, okay? And then once we get a certain amount of venous return, we'll talk a little bit about contractility and things, and why altering preload is going to alter contractility. And as that goes up, we're going to get more, okay? So, if you look up in a medical physiology textbook, preload, it's going to call it end-diastolic pressure. What end-diastolic pressure refers to is if you fill a certain amount of blood into the left ventricle, there you can measure a certain amount of pressure inside the heart, okay? The higher that pressure goes, the larger the pressure gradient will be between in the left ventricle and the aorta, and between in the left ventricle, the aorta, your brachial artery, your femoral artery, et cetera, et cetera. Blood and all fluids in our body moves via pressure gradients. So if we can make the pressure gradient bigger, okay, then we're going to move more blood from one place to another. So we make preload bigger, end diastolic pressure goes up, okay? That's also going to then determine the extent to which the left ventricle, or the chamber of the heart, is stretched during filling, okay? Think of the left ventricle like a balloon, okay? It has a certain volume to it, and we can fill it up to a point, but you can also, it has a level of elasticity in the cardiac muscle. And so it can fill up, and then it can stretch out a little bit, okay? Not a huge amount, but it can stretch out some. And so you may think, oh, I'm gonna overfill the kind of measured relaxed volume. But if we do that, that's gonna actually be of use to us, okay? So as we stretch, as preload increases, we're going to invoke something called the Frank-Starling mechanism, or the Frank-Starling law, okay? And that is going to kind of describe this graph that we see here. Ventricular performance. This could be strength of contraction, or it could just be stroke volume, okay? This is how much blood is leaving the left ventricle. Here is ventricular end diastolic volume. So this is the extent to which we are filling. So this is preload. As preload goes up, ventricular performance goes up. This graph is called the Frank-Starling graph. Okay, you can call it this. So, why does stretching help? I am rhetorically asking. Megan, stand up. Megan, can you jump up and touch the ceiling? Okay, that was too easy. Thank you. What did she do before she jumped? She squatted. It's a counter movement. Okay? Your heart, every time it gets sort of an increase in preload, has a counter movement. The stretching is a counter movement. Why does the counter movement increase the force of contraction? Why does the counter movement let Megan jump higher? Why does it let the heart contract more forcefully? Like a stiff tension. Very good, Cal. So as preload increases due to an increase in venous return, the left ventricle fills, it gets stretched, and so you've got contractility, so you've got the force of contraction from the muscle itself plus some stored elastic energy, which is why this is not kind of a one-to-one sort of deal. Okay? Y'all with me so far? Okay, very good. Hey, it appears the thing has returned today. Lovely. Okay, so if we look at all of this, if our goal is in many ways to stretch the myocardium, so we want to stretch the left ventricle, these are going to be things, as we've already talked about, right? All of these things, except for maybe heart size, are going to be factors that can affect preload. They're going to help us to stretch the myocardium. So cardiac output and venous return, okay? So greater the amount of venous return we're getting kind of per cardiac output. So the more return, the greater preload. So this can be a little bit of a complicated thing, But as you raise your heart rate, your cardiac output begins to go up. As that cardiac output goes up, you're actually circulating more blood, or the same blood more often. And so that's going to have this natural effect as cardiac output raises, that there's going to be more blood coming back into the heart in a given period of time than there was before. That will lead to, that is going to promote greater return and give us a little bit more preload. Okay? Total blood volume. People that have more blood to get returned to the heart. Stretches the heart more. Okay? You guys will see. All the things that we do during exercise are going to help us from a venous return standpoint. One of the big changes with exercise training, okay, is you may expand your blood volume by 15 to 20%. Okay? 15 to 20, you may gain a whole extra liter or 1.5 liters of blood. Having all of that, imagine I gave you an infusion of 1 liter of blood and your heart's the same size. You've got more blood to move around. You force more back in there. And so it's going to make preload go up. So one of the things that happens as you dehydrate yourself, when you sweat during exercise, is your blood volume falls and your venous return is going to fall because your blood volume is down. And therefore your stroke volume may fall. Your heart rate's going to have to go up. You'll evoke something called cardiovascular drift. And now your VO2 max has gone down because your cardiac output's screwed. Okay? There's the muscle and thoracic pumps. So we can have Keldon do some squats for us. And if we remember what the anatomy of the venous system looks like, veins have valves in them, and veins tend to be have lower, much lower pressure in them. That combines to let us do two things. When you contract a muscle, it squeezes the veins. The muscle contracts, it raises the pressure around it, it squeezes the veins. Okay? The veins are low pressure, it's easy for them to get collapsed. I apologize, it probably freaks people out, but maybe you can see veins in my arm. Like, I can just do this and squeeze them, and I can close off those veins. Okay? I can't, I mean, I could, but I have to press a lot harder to like close off my brachial artery or something. But the brachial vein, we can close that sucker right down because the pressure's so low. So every time you contract, you squeeze the veins. It's like squeezing toothpaste right in a toothpaste tube. Squeeze, squeeze, squeeze. They have valves. Blood moves forward in a vein. It cannot ever move backwards. If it moves backwards, we got big problems. Okay? It moves forward. So every time you contract and you squeeze in those muscles, it drives blood forward towards the heart. That's one of the reasons when you get done doing high intensity exercise, they say make sure you walk around. You need to keep doing the muscle pump because you've got all this vasodilation, all this blood going everywhere. You've got to keep walking so you can keep getting blood back to the heart so that you can maintain cardiac output and maintain blood pressure, or you're going to pass out, right? Don't be dumbass Dr. Black who finishes his dissertation and defends on one day, and then like 2 days later, after having not really exercised because I was doing my dissertation for like 6 months, agrees to do an experiment for somebody, and I do a VO2 max test on a bike, and I'm so freaking mad because the bike seat is uncomfortable, and I know that I'm so out of shape, and I'm really pissed. And we get done, and they're like, Chris, okay, now you need to recover. And I'm like, no, I'm getting off of this bike. Like, I don't care. My butt hurts. This thing is uncomfortable. And like, I just get off the bike. And guess what happens? And I pass out. And they laugh at me. I'm like, I know that's my fault. It's my bad. I knew better. Venous return. Okay? Gravity, so posture affects things. When you're in an upright position, right, the heart is up from gravity, and so a lot of the blood tends to be in the veins during your lower body. So blood has to move up towards the heart against gravity. So if we lay you down flat, okay, you're going to get greater venous return because you're not having to work as much against gravity as before. If we do crazy things like your Batman and I invert you, right, and I hang you like from your feet from the ceiling, and you're down, now gravity is helping with venous return. And so that's going to make preload go up. That can actually make things better in some ways for all of that, despite the fact that you're hanging upside down. There's a whole other issue then. Now your afterload is going to go up though by doing all of that, because now getting blood out of the heart back to your legs has to work against gravity. It's easier coming back in, but it's more difficult going out. And so that can that can cause some different problems. So, Megan.
So what's your take on like, all those years coaches were like, oh, like don't lean over, don't squat down when you're tired, like recover standing up. But now there's controversy like, oh, you can like bend over and it's fine. Like
the standing up was just, it's easier to breathe when you're up, right? You can get greater, you can kind of open your chest cavity up to a greater extent, right? You're not going to be like all of that. Like that doesn't, so many things.
Do you think it has any effect on like venous return if you're standing or squatting or anything like that?
I'm sure that it does, but the question becomes, I don't know you're done exercising, what does your venous return have to do with anything, right? That's always been my thing. Like, I don't really know, like I'm here and I'm recovering, am I going to have to go again in 30 seconds? Then maybe it matters, right? But I just ran a race and I got a half an hour till my next race. Like, who cares if I want to lay down? Like, if I fall down or not, or if I walk or I don't, like within 10 minutes, we're going to be back, the lactate's cleared, we're back to kind of regular sorts of things. So that's, to me, is the idea is that this raises, right, it's going to help open for breathing to be easier. But I suppose if you did this, I don't know that we're really helping venous return any more than doing this. I guess it's a little bit lower, but it's got to kind of come up, and I don't know. The continuing to do the muscle contractions afterwards is the thing that really does seem to help continue with that muscle pump to make sure that venous return gets that way, so that you can have some time to adjust blood pressure, you can adjust vasoconstriction in those peripheral arteries, so that you're not flooding all of that blood down there. So, kind of like the power plants, right? Jake?
You might not answer this, but is this the reason, like, the muscle pump as well as like venous tone and posture with gravity? Is that the reason why I know that, like, in the Army, parachuters have to, when they get stuck in a tree or something like that, they're told to run while they're stuck in a tree, because if they don't, doesn't their blood just kind of
Pool down in their legs?
Yeah, and they don't correctly finish returning, so they die just by like.
I had not thought about that, but yes, that could definitely be a problem.
Yeah, because I was thinking about that, and I was like, well, there's this like games at carnivals where they're like, hang by your arms for 3 minutes, and then that's like, would that be why it's so difficult after like a while, because you're just having a really hard time if you're not moving while you're
so there's a whole separate kind of an issue. We will get into very briefly a little bit later on, but it's at a force level that is about 30%, 25 to 30% of your maximum capacity. The force generated by your muscles is going to be sufficient to exceed even with the pressor response is going to be sufficient to shut off systolic blood pressure. And so, like, you hang, I'm exerting force, and so then I get no blood flow to my arms. So that's probably why I stop over time, is that I'm getting no blood flow, so then I become anaerobic. We find that women tend to be a little better at that than men, for a host of reasons, and which is why women are less fatigable than men in some instances. We kind of match them on strength and muscle size and body size, and they look basically the same per state of training, but in general, women are less fatigable than men. I had something else I was going to tell you now. So,
sorry.
And that's okay. I don't know what kind of carnivals you're going to where we're like doing like hang from things, and I got to get out more apparently.
The Kansas State Carnival has it every year where you can get like bike if you can hang for 3 minutes. Like,
really?
Yeah, like a bike. And one time it was a moped, and like nobody could do it. The bigger you are, the harder it is. That's what they
it is bigger. I mean, you weigh more. There's more gravity.
Yeah.
You can use any grip you want, or do you have to be over?
No, you can do whatever grip you want. You just have to hang there
It's hard.
for 3 minutes, and it's like it sounds easy, right? Everybody's like, oh, 3 minutes, I can do that, and then you get to about a minute mark, and like, this hurts, and about minute 30, you're like, I can't do this anymore.
You know why, right? Because
Yeah.
the problem is I got no blood flow to my hands, and so I run out of ATP in my hands, and I can't hold on anymore. So, yeah. Okay. Heart size matters. Less so from a venous return standpoint, but just having a bigger heart means you can put more blood into the left ventricle. Right? You guys will hear me say this when we talk about endurance exercise. and it's like the ultimate like dad joke in some ways, but the person, all the things being equal, the person with a bigger heart has the bigger stroke volume. If you have a bigger stroke volume, you're going to have a higher VO2, so you win the race. So, Chris Traeger from Parks and Rec style, literally, the person who literally has the biggest heart wins, right? Literally. That's the thing. So heart size matters. Then we talked about venous tone, if you can adjust kind of venous tone. So we didn't talk about the thoracic pump, but as you breathe more deeply and you expand the chest cavity, the pressure inside falls to a greater extent, and it creates this. I mean, it's not a faux kind of sucking, but it's like almost like a negative pressure, but it helps. With pressure is less from the outside of the veins is much less up here than it is down there, and it creates almost like this kind of vacuum effect of helping to pull blood up and back towards the heart. So you can imagine muscle pump and thoracic pump are going to get activated during exercise. Cardiac output goes up during exercise, right? Posture doesn't change very much. Venous tone can change if we needed to in the midst of this. So you guys want to guess what happens to stroke volume during exercise? Kelvin? It goes up. That's right, it does. It goes up. It absolutely goes up to a point. Okay? So we talked about these things. We talked about the valves. All right. So let's now talk about afterload. Okay? So preload is what's in there when we start, right before it contracts. Afterload is the opposite. Afterload is how much is left in the left ventricle at the end of contraction. Okay? So if you have a high afterload in the context of what Alex was talking about, you're going to have a relatively lower ejection fraction than a person that has a lower afterload. Okay? Now, weirdly, afterload or if you have high afterload, that's going to tamp stroke volume down. So we want preload to be as big as possible. We like afterload to be as small as possible in our efforts to maximize stroke volume and therefore maximize cardiac output. Okay? So afterload can be affected by sympathetic and parasympathetic input. It can be affected by static muscle contractions, anatomical impedance, and intrathoracic pressure. So if the pressure changes in a certain way, then it's going to become more difficult to get blood out. Okay? So this is the thing, okay, about blood pressures and fluids and things that I don't like. The naming convention is strange until you get used to it. Okay, so I always ask anybody, but Pearson, you had physics?
I have.
Okay, did you get to take the calculus-based physics, the easy kind?
Yeah,
it was calculus-based, right? So took physics 1 and 2, and I was in college. My roommate was a physics major, and he would laugh at us and be like, "Oh, you just take the derivative," and I'm like, "Shut up." And over here, like resolving vectors and doing all kinds of trig and stuff. You just take it, and I'm like, "Shut up," and no one cares. Okay, so when we talk about the physics of the movements of fluids and gases, okay, resistance is the idea of how difficult it is to move something, okay? And so we want, if we want flow or movement to be high, resistance needs to be low, okay? So if we lower the resistance, which we will talk about as we exercise, we lower something called peripheral resistance. So we make it easier for blood to move into other parts of the body. As resistance goes down, afterload will also go down because it's easier for blood to leave the heart and go someplace else. Okay? So afterload is really the product of all of the things that are going to play some role in the resistance to ventricular emptying. Okay? So if we have an increase in afterload, that means that peripheral resistance is going up, and then that means the heart has to work harder to overcome this increased resistance, right, to make our afterload get smaller and get back down to where we need it to be, okay? So the easiest way to think about some of this, okay, is to think about blood pressure, right? If I have a person that has very, very high blood pressure, I'm a hypertensive person, okay? So imagine that the blood pressure in my aorta, okay, is, let's say, 200 millimeters of mercury. Okay? 200 millimeters of mercury. That means that in order for blood to leave the left ventricle has to contract and raise the pressure inside the ventricle to at least 201 millimeters of mercury. Okay? Otherwise, it's not going to leave. That means it has to contract more forcefully to get the pressure to there. You have a normal person who, let's say their aortic pressure is 120 millimeters of mercury or 100 millimeters of mercury. The heart has to get the same amount of blood to leave, okay, the heart doesn't have to beat nearly as forcefully, right? And so because of that, then people that have high blood pressure have that, the increase in blood pressure provides resistance against which the heart has to work. And so when you have high blood pressure, then that's going to make the afterload is going to go up. It means less blood is going to leave for any amount of pressure that's generated inside the left ventricle. Okay? So exercise involving very high force production tends to increase afterload. So resistance exercise tends to increase afterload. Okay? Which is not really a huge deal because a lot of times when we do resistance exercise, it's not something that is limited by blood flow to the working muscles, because you're going to either do a rep and relax and afterload falls and you're going to get back to normal, or you're going to do several reps, but you're going to have enough energy. You're not really limited by the things that would be in circulation going around. So when I do resistance exercise, blood pressure goes way up, oftentimes because of Valsalva, right? I'm going to raise intrathoracic pressure, and that's going to raise my blood pressure, and those two things in conjunction are going to make the resistance to flow coming out of the heart very, very high. Okay? Now, any of you remember? Ryan, do you remember from Dr. Mike's class or Dr. Jay's class, whoever you had, what happens to blood pressure during exercise? It does go up. The correct answer is it depends, right? It's always it depends. Diastolic pressure does one thing. Systolic pressure does another. Well, I guess diastolic pressure did what systolic pressure is supposed to do. You're about to die. And so that is no bueno. That's an absolute contraindication to exercise. Stop, do not pass go. Call the cardiologist right now. So systolic pressure rises during exercise. Diastolic pressure tends to stay roughly the same. So you may say, like, that seems backwards. If systolic pressure is increasing, isn't that just going to increase resistance to flow? And would that not increase afterward? Would that be a bad thing? And so what I can tell you is that we can raise blood pressure without having to raise afterload, because as cardiac contraction strength goes up, pressure in the ventricle goes up, so that's going to make pressure in the aortic go up kind of right during that. But as long as diastolic pressure doesn't change, then during diastole it's going to be okay. And we're going to vasodilate everywhere else. We're going to drop peripheral resistance in these things, and so they kind of offset each other to make that be okay. But that's the big issue. People that are hypertensive, or people that are doing lots of Valsalva, where you hold your breath, right, when you're going to squat. I'm not telling you don't do that when you're trying to squat. You may completely squish your liver or something, right, if you don't do those things. We need to Valsalva so that we have something against which to work, so we don't like squish all of our internal organs. But that can lead to very, very high afterload. If you have high afterload, the heart has to contract more forcefully, as you guys will see. That can lead to what we would call concentric contraction cardiac hypertrophy, which is bad. It leads to thickening of the walls of the ventricle. They become less stretchy, and they become more prone, okay, to actually being in a place where we can have cardiac arrest. Okay, so that's one of the bad things of having people that have high blood pressure. That's afterload. Okay. Okay, now let's talk about contractility. Contractility is the strength of cardiac contraction. Okay. Quality of ventricular performance at a given level of preload and heart rate. all that this means is it's the strength of contraction. If I make the left ventricle contract more forcefully, I will eject more blood because I will raise the pressure in the ventricle to a greater extent. Okay? So, you guys will remember that we said that we can have sympathetic nervous system stimulation of the left ventricle. So, epinephrine, especially norepinephrine, are going to increase cardiac contractility. There can be other, what we call inotropic agents that can increase contractility. All right, inotropic agents are just things that would raise contraction, like raise contractional strength, or raise heart rate potentially. Hypoxia, which can happen if you have blockages, let's say in your coronary arteries, is going to decrease the strength of contraction. Acidosis, which often accompanies this hypoxia. The heart is so good, it has so many mitochondria, okay, that the only time that it's ever really going to make lactic acid is if you're in a position where it has become hypoxic, which basically means you're having a myocardial infarction, you're having a heart attack, okay? And so that's no good. Tissue death is going to decrease all of this. So these things kind of all cluster together. These are more pathological conditions that we're going to get in a lot of instances, okay? That's maybe when Kelvin throws way much on there on the bench press. His pecs contract so forcefully that they're going to squeeze all the way like under his ribs, and they're going to squeeze on his coronary arteries or something, and he's going to get a little bit hypoxic there. I don't know. I doubt that's the case, but let's hope not. Right. Let's hope not. Okay. So all of this stuff together. So when you exercise, sympathetic stimulation goes up. Okay. These things tend to not really happen, and so I'm going to make the heart contract more forcefully. It contracts more forcefully, then afterload is going to go down. When afterload goes down, actually it can help make preload go up. So there's this kind of all kind of working together. These are going to be what we're going to call Frank Starling curves, and they are showing this is ventricular end diastolic volume and stroke volume, right? So this is basically the amount of blood that gets ejected for the amount of blood that is in the ventricle at the end of diastole. And so this curve here is for a very fit athlete. Here is what maybe would be a person that has heart failure, has congestive heart failure that's way out here. Here is, you know, a somewhat kind of recreationally active person, and then maybe a sedentary person is going to kind of fit in here. And so stroke volume regulation is the combination of all of these different things together. Okay, they're all kind of working together to help us determine what stroke volume is going to be. Then the last one of these we need to pay attention to only really matters under very certain circumstances. Okay, it may only matter at very high levels of exercise, very high exercise intensities, and that's going to be heart rate. Okay, and so one of the weird things that happens is as you increase heart rate, the amount of time the ventricles or the atrial chambers spend in diastole, the amount of time that it takes for them to fill up, is going to decrease. As that decrease happens, there is a chance that preload will fall because we just physically do not have enough time to get as much blood into the ventricle as we did beforehand. Okay? And so what you can see here is that here we have people, this is, so don't worry about these curves. We were trying to show, this is a really famous paper from 1986, and you can look at all of these are all individual data. This is what my graph pad would have done, right? Is it would have made these lines, and you would have had all these little dots on here that would have actually represented it. So this is everybody that was getting tested, and this is, I think these are direct measures, so they've got like central lines running in these people, and they're directly measuring sort of stroke volume and trying to measure end diastolic volume. You could maybe measure those things as well if you wanted to do like do an echocardiogram on them as well. But the curves kind of look like this, and embedded in all of this are people that are highly trained, people that are very untrained, and people that are kind of recreationally trained, which is these three sorts of things. But what you can see is what is happening at kind of walking down here, like 25% of VO2 max, here's 100%. So here's in systolic volume, here's in diastole. So this is filling, this is afterload. So preload, afterload, stroke volume. out of all of these things. And you guys will note very famously here, stroke volume increases during exercise to somewhere around 50%, 60% of exercise intensity, and then it levels off. And then you may note that in some of these people, it looks like it's beginning to kind of fall off a little bit at very, very high exercise intensities. And indeed, that is the case. And it tends to be a little bit more pronounced in untrained people. And this is because as you near age predicted max heart rate, and there's some arguments, although I've not seen any kind of recent data, that this may be even more pronounced in younger people than in older people, because you often have a higher heart rate, that heart's beating so fast, filling time decreases, and so preload decreases a little bit, and that's going to drive down stroke volume. These are some data where these are the same people, and they were untrained to begin with here in the white, and then they trained them. And what you can note is that stroke volume went up, and some of the decline that happens near max exercise also is attenuated to some extent when you're more trained. So it tends to be much more pronounced in untrained people. Okay? So there we go. So heart rate can, under kind of high exercise intensity standpoints, reduce stroke volume. Okay. Questions about that? I hope you're all thinking about wonderful essay questions that I can ask you about all of this. We're going to manipulate one of these, but not the other one. All right, like here's some drugs that affect this, but not this, or I don't know. We're going to like take and we're going to do a heart transplant from Cali to Keldon, and then what's going to happen, right? Like in the midst of all of those kinds of things, there's a whole host of stuff that we could try to manipulate around there. Okay, but we will build upon all of that when we get into the second lecture, when we talk about the changes that take place during exercise. And you have to appreciate those things. And we can work in based upon that, what happens if you get dehydrated, what happens if you take a blood transfusion, what happens if you're going to try and counteract dehydration by drinking fluids and things. It has these very predictable effects on blood and blood volume, which can affect preload. And so if we can do that, then there's all of this kind of things together. Okay, blood. I feel like blood is I always hate the term the redheaded stepchild, but like blood is the underappreciated like little brother in those ways. So, Callie, are you a redheaded stepchild? Like literally?
I feel like it. No one else in my family has redheaded.
Okay, but you're not actually like.
No.
Okay.
No.
So these are some of these interesting things. So my wife, bless her, I love her to pieces, but she was in college. Her parents got divorced when she was in elementary school. She was in college before she realized she was a statistic, that she was a child of divorce. And like that was a special thing because her parents continued to get along, and they there were not like these wild, crazy custody battles, and she saw them all, and she played volleyball in high school and they would do things, and it wasn't that she was like, oh my God, like whatever, I should maybe be more messed up than I am because stats tell us I'm a child of divorce. Anyway, so I had a point to that, but like she's not a stepchild, but she is redheaded, and so I don't know where I was going. I need a better thing, right? I don't know. Like, what's the underappreciated like form of social media now? Pardon? MySpace. Okay. Yeah, but it has to be important. I don't know. Is Facebook important? I mean, it is in a lot of ways, but right, one of them is like TikTok, and one is Insta, and this other thing, somebody's Snapchat. Blood is the underappreciated portion of the cardiovascular system, I feel like. Okay, it's really, really important, and it has some very special characteristics, especially of red blood cells and things that make it really useful and really good for what it does. But I feel like we don't talk about it. We spend a lot of time talking about central circulation and control of blood pressure and changes in kind of the pump and the vessels, and we never really talk about the stuff that's going through there very often. Because I assure you that if this stuff gets messed up, then it doesn't matter what happens with anything else. Okay, so let's talk about that here for just a little bit. So its primary function is to transport things. Okay, oxygen, CO2, lipids, glucose or carbohydrates, hormones, right? There we go. The hormone thing makes more sense when Dr. Deb is actually also concurrently teaching the endocrine class. We are not doing that this semester. We're not going to talk about it very much, but the blood also helps us to regulate temperature. And we will talk a little bit about all of this, even though it is maybe my least favorite thing, is the idea of how we can use the blood to help buffer and balance acidity in conjunction with the pulmonary system to help us maintain proper pH. Okay? So we've talked about blood volume. It varies across people. It's very much related to body size and your state of aerobic training. So the bigger you are and the better you are trained, the larger your blood volume. And that is good for all of these different things. Okay? It's good because you have more red blood cells. It's good because you have more plasma. So you're going to be better able to sweat some stuff out to help regulate temperature. You've got physically more red blood cells, so you can physically put more oxygen and in some ways then more CO2 because you're going to bind some CO2 to hemoglobin. Afterwards, you can put more oxygen in the bloodstream, which means there's a greater chance that you can have a bigger O2 gradient from the capillaries into your muscle fibers or to your brain tissues. Okay? Okay. So blood is, a plurality of blood is water. Okay? So somewhere between maybe 55 and about 70%, depending upon a host of things, of your blood is just water. Okay? We call that plasma. Now, there's a difference between plasma and serum, and we're not going to really get into all of those kinds of things, but plasma is basically water and a few plasma proteins and a little bit of other stuff. Okay? The non-plasma, or really the non-water portion of your blood is collectively termed hematocrit. Hematocrit is the blood cells, okay? More than 99% of which are red blood cells, okay? As long as you don't have leukemia or some kind of really powerful active infection, your white blood cell count is going to be probably less than 1% most of the time. Platelets are going to also be there. So most of the cells in your blood are red blood cells, which is good because it lets you carry a bunch of oxygen, okay? So in Dr. Deb's class next semester, maybe even then if you took exercise phys lab as an undergrad, we can measure your hematocrit percentage. We can do some things and figure out what percentage of your blood is basically red blood cells, and then what percentage of it is plasma, okay? And there are some things with training, there are some things with acclimatization, there are some things with altitude, and whether or not you're Lance Armstrong and your blood doper, that can affect the percentage of red blood cells as a percentage of your whole in your blood volume. Okay? Ladies, if y'all are anemic, sometimes you can have lower hematocrit percentage of things as well. Okay? So you're sort of smirking under your mask there. What are you thinking?
Lance Armstrong, yeah.
Lance the doper?
Yeah.
Yep. That's right. I'm just telling you, get us some EPO on the black market, man. We can get some red blood cells. We'd be in good shape. Okay? So, just saying, you want your VO2 to go up real quick. Let's do that. So, other parts of red blood cells, why are they so important? Why does it matter? Why would changing your hematocrit percentage matter so much? Okay? So, a red blood cell is termed an erythrocyte. Erythrocytes and red blood cells have a half-life, I think, of somewhere usually between a life of about 90 to 120 days. So you're always recycling these red blood cells, okay? But the primary function of a red blood cell is to carry oxygen, and they are uniquely and spectacularly well suited to do this, okay? In a red blood cell, there is going to be this thing called hemoglobin, which I'm sure all of you have heard of. Okay? Hemoglobin has iron in it. It's like a cytochrome. So it's very strongly attracted to oxygen. 4 molecules of oxygen combine to each hemoglobin. You have about 250 million hemoglobins per red blood cell. So a red blood cell can bind up to about 1 billion molecules of oxygen. So you take 1 billion and you multiply it by however many million red blood cells you have in your body, and you get this giant ass number. Okay? This is good because it means you can bind and move around a much, much larger amount of oxygen than you normally need for function all the time, okay? It's a really, really big safety mechanism, okay? So red blood cells are really important. Okay. That's it. We're going to move on from our somewhat maligned little brother or little sister in that particular way, okay? We're going to start talking about the vascular system. The pipes, if you will, okay? The pipes are the tubes in which the blood is going to move. So there are three, or really, if you want to even break the three into five kind of main kinds of blood vessels that are going to exist in the body, okay? There are arteries which serve to carry blood away from the heart. There are capillaries that are going to be these very, very small blood vessels. They're oftentimes only about 1 red blood cell thick, that are going to be in and around all of our tissues where gas exchange and nutrient exchange is going to take place. And then there are veins whose job is to bring blood back towards the heart. If we want, we can take arteries and break them into what we would call large arteries, and then conduit arteries, and then we can have these things that are called arterioles, really smaller branches of arteries, okay? Think of arteries, and in that same way, veins is like they're branches on a tree, okay? Your big main arteries are the trunk of the tree, and then the arterioles are all of the little branches that are coming off of all of them. So all of these are very important. They're all very important. We're probably going to spend a disproportionate amount of our time in class talking about what happens with the arterioles, okay? These are smaller branches of arteries, and the reason that they are so important is that these are the arteries that we're going to be able to change the size of most readily. And so because of that, the arterioles are going to help control which capillaries in your body are going to get blood. And so because of all of that, we oftentimes refer to arterioles as resistance vessels, okay? And so the arterioles, by changing their diameter, will control how much blood goes to a particular tissue in your body. So where is the blood in your body right now is controlled by the arterioles leading to every tissue. Some of them are going to be what we call vasoconstricted. They're going to be very small. When they are small, the pressure in them is high, and that's going to have lots of resistance to blood going to that tissue. Where you're going to get the most blood is where the arterioles are vasodilated, the pressure inside of them falls, that lets more blood go there. Okay? So as we begin to exercise, arterioles become particularly important for us because we're going to kind of play around with which ones are open and which ones are closed at a certain time and why they are, to help us push blood to the tissues that need it and push it away from the tissues that don't need it. Okay. All right, so here's the vascular system or the vascular tree, if you want to kind of talk about those things. Key things to keep an eye on inside a blood vessel, okay? On the arterial side, it's going to be much more pronounced, okay? But we are going to have smooth muscle that surrounds these arteries and these arterioles, okay? Here's our smooth muscle layer. It's going to be out here, okay? You're going to have a little bit of smooth muscle, not much in venules, but maybe a little bit in your veins. It's this smooth muscle and its ability to contract and relax that changes the diameter. Another thing to keep an eye on is this inner lining, this inside layer of cells here. It's called the endothelium, okay? The endothelium. These are the magic cells that control everything, okay? The endothelium. These are the cells that if you put atherosclerotic plaques over the top of them, you cease to be able to control the diameter in some of these cells, and so you can't regulate blood pressure very well, okay? But the endothelium is going to be really, really important for one of the ways that we can make decisions on how dilated or constricted these arterioles and arteries are. Okay? All right. So here's our arteriolar tree, right? Primary arterioles, secondary, tertiary coming off, fourth order ones, and then these terminal ones, the little small ones, all these little things that are running this through, these little hair-like looking things are going to be capillaries that are going to be there. Okay? It literally looks like a tree branch, right? Like I was not lying when I told you it was like a tree. I had seen the picture previously. Okay? Okay. So the other thing that we need to talk about is we talked about the endothelial cells. We talked about the smooth muscle. What we have not talked about is something called a plexus of perivascular sympathetic nerves. So arterioles and arteries to some extent have sympathetic nervous system innervation. Okay? So just imagine that all of the arteries and arterioles in your body have these little nerves that are going to go to them. And they can release epinephrine and norepinephrine, and that's going to have an effect to tell them to contract. Okay? So here we have the vascular smooth muscle that is surrounding our arteriole, little Michelin tire man looking things here, little bands, right? Okay. So here they've taken this and they've just dissolved away the actual blood vessel and the smooth muscle, and you can see they've stained for these are the sympathetic nerves that are going to connect to and tell all of the smooth muscle to be able to contract. Okay. So you have this vast network of sympathetic nerves that are going to go to all of your blood vessels. Okay. So okay, we're going to get back to this. So we'll stop. Because once I start talking about blood pressure, then we need to be able to finish off then some blood distribution stuff. So, okay. We'll get into Ohm's law and Poiseuille's equation and all of that. Okay. So we will be good. We'll still be good for next week. On Tuesday, we won't have a quiz again. We probably won't. Light being a place to do. We probably can finish all of this up on Tuesday of next week. So we probably have your critical thinking questions done next Tuesday. Okay. Sweet.
We could have taken a picture of a tree outside and noticed the arterials. I looked at that and some more.
Right? I mean, it's crazy. Okay.